Hi, I'm Lange. I'm Vice President of Artificial Intelligence at Unity Technologies. I've really been looking forward to this event since this is my first time at Shift. I have an exciting talk in store for you. It's about getting on the road to artificial general intelligence. My talk is more about the journey and less about how long time it will take or what we will find when we get there. So let's get started. Please allow me to introduce Unity Technologies. We offer a real-time 3D platform that is used for gaming, AR, VR, film, automotive, robotics. Actually, over half of the world's games are being developed on the Unity platform. We have seen installs of over 4 billion devices, and we have over 2 billion monthly active players playing a game written on the Unity platform. And we have 3,000 employees headquartered in San Francisco. So you can say we are the most popular gaming company out there. So what does games have to do with this? Well, games have been playing a big role in the research of AI for a very long time. It started as early as 1950 when Claude Shannon, he published an article about how to implement a computer game to play chess. We have seen other examples where games perform at world-class level. Chinook, which is a checkers program from 1989. We have seen Deep Blue when I was at IBM in 1997 when it defeated Garry Kasparov in chess. And more recently, from 2011, there's an example of IBM Watson winning Jeopardy. All these examples are characterized by really smart implementations by really smart people. If you take the Watson example, it's really a big database of curated questions and answers. Yeah. In 2016, there's a change with DeepMind's AlphaGo. We're now moving to a phase where these game algorithms are generic learning algorithms. They're being trained to play a game. They're not being implemented with a specific strategy in mind. We have seen a lot of video games now being used to advance AI. We all remember the entire games, both from DeepMind and OpenAI, and a whole range of other games, including Minecraft from Microsoft. And very recently, Unity's own obstacle challenge to improve reinforcement learning. So what is it with video games that actually link them so much to AI? Well, let's ask the question first, what is intelligence? This is the dictionary explanation. It doesn't mean too much to me. So what is the real intelligence that we truly know? Well, it's the intelligence in biological systems. Let's take a step back and look at biological systems. Essentially, the idea of senses and computation in nature that allows us to consume, eat food, to get energy, to avoid getting eaten while we are trying to get food, become more abundant because no individual lives forever. We need the species to keep the species going, and we need to be aware of physics, in particularly things like inertia and gravity. Don't fall down from the tree while you're trying to pick an apple. And finally, agency, the ability to change the environment. Yeah, this is the competition. This is the real game of nature. Yeah, and what nature then did is it actually invented what you just saw here. It invented lots of infrastructure to implement the needed intelligence to survive in this game of nature. Yeah? So chemical mechanisms, cellular structures, multicellular organisms, and so on. Yeah? All these things were evolved in nature to basically create the foundation for intelligence. Yeah? So when we look at a real-time 3D engine like Unity, It's a spatial environment with a physics engine, and you have a self-sufficient ecosystem that actually pretty closely replicates the real world. Yeah. You can say that you, with Unity, have a private AI biodome. Yeah. So Unity allows you to build your own AI using a toolkit called Unity ML Agents. It allows you to build your 3D environment with a physics engine, train your machine learning models, and deploy it on a device. Yeah? So in this case here you have trained a virtual dog, go fetch the stick. ML Agents is an open source environment, or open source toolkit, sorry, with a bunch of environments that you can basically experiment with. Here's the URL for the GitHub repository. You can take a picture here if you want to visit it later. And here we have a couple of references for papers that we have written about ML Agents and the Obstacle Tower Challenge. Now let's go into these learning scenarios. Yeah? So you build these environments with ML Agents, and now you're going to train your agents in these environments. We emphasize what we call the nature's learning method here, which is reinforcement. It's basically observing the environment around you, taking an action, and reap the rewards or the punishment, the negative rewards from that. Yeah? And nature is in a way constantly moving from exploration towards exploitation. Yeah. So when you move around in this flywheel between observation, action, and rewards, you learn and you become better and better through exploration so that you can exploit. Let's take an example of that, if it's a little too abstract here. At Unity, we wanted to figure out if we could teach a chicken to cross the road from scratch, from Tabula Rasa. So using a generic reinforcement learning algorithm as I just described. So in this case here, the system can observe the pixels frame by frame, just as you do. There are 4 actions, left, right, forward, backwards, and there's a reward signal. The chicken, a negative reward if the chicken gets hit by a car, and a positive reward for picking up gift packages. Yeah. Now let's look at this video. It starts from scratch. The chicken has no idea, the algorithm has no idea, it's just a learning algorithm. And you can see it moves more backwards than forwards. But in a moment it will fetch the gift package up on the right here, and then killed by a car. What did it take? 5-10 seconds and 2 bits of information. Yeah. After half an hour, you see the chicken actually gets pretty good at picking gift packages and avoiding the cars, at least for a few seconds. Yeah. But as you will see, when it trains more and more, it gets better. In this example here, we let it train for 6 hours, and now watch. The chicken became superhuman. Yeah. It will pick up packages and it will never get hit by a car. Yeah. Incredible. From Tabula Rasa, from scratch. Now, let's go in and look at some specific scenarios that you can play out with ML Agents. So let's take control learning. Here you actually have 4 legs, so it's 8 joints that need to operate in coordination to move forward. Using reinforcement learning, these quadrupeds, they basically learn to walk. Yeah? Here's a humanoid. Think about a small child, 12 months old, learning to stand. There's a lot of joints. And again, here's an example of reinforcement learning, trying to learn to coordinate those joints to remain standing. Yeah. Or walking, for that sake. Let's look at some other very well-known learning approaches that we as humans recognize. So let's talk a bit about curriculum learning. So in this case, I want the blue agent to jump the wall. When the wall gets too high, it needs to use a tool, which is the orange box. It needs to push the orange box next to the wall and use it as a stepping stone. Yeah. We have found that if you use a curriculum, you start easy, and then you, as the agent graduates, you incrementally make the tasks harder. And basically, progress depends on graduation. In this example here, you can see how curriculum learning, which is the blue line, basically learns faster and learns better. Whereas if you just throw the computer in the deep water and give it the most difficult challenge from the beginning, it takes a very long time to learn and doesn't learn very efficiently. So take a look at this example here. Pretty impressive. The blue agent learns to push the orange cube next to the wall to use that as a stepping stone. Look, incredible. It's really using the cube as a tool. There are other examples of features in learning that we recognize very well. One of them is memory. In this case, the blue agent comes in. If the cube, the big cube in front is orange, it should use the orange exit. Otherwise, it should use the red exit. Look at this here. We don't tell it that the color actually matters. It learns that that orange means orange exit and red means red exit. Yeah. There's no software engineers here programming this. It's basically by trial and error, over and over, it figures out what matters. It's not the size, it's not the location, it's the color that matters. Let me show you an example, another example that we recognize, which is hierarchical learning. It's basically navigation and control. In this case, there's one machine learning model that basically keeps an eye out. It uses ray tracing here, keeps an eye out for the target, and basically you can imagine it says left, right, straight, left, right, straight. Try to navigate the legs. The legs are what I showed you. It's another model. It's what I showed you earlier. It's the quadruped walking. So we basically have a split of responsibilities here in the hierarchical model. Multi-agent learning. Now, that's interesting. In this case here, we have two agents helping each other. They basically play to each other. The reward here, it's collaborative. The reward is to keep the ball in the air and not touching the ground. We became a little more ambitious, and here's an example of soccer. We essentially train one player to be offensive, another player to be defensive, and we train them up against each other. Yeah? And then the offensive player is basically being rewarded for scoring. The defensive player is being rewarded, or rather punished, if they're being scored upon. And when you have trained your agents and they don't get any better, you basically copy them or clone them and create two teams of each two players, and it looks like this. These guys are playing against each other. Notice how the defensive player became what we recognize as humans as a goalie, and the offensive player become more like strikers moving around. Yeah. Let me show you another example where we don't assign roles to the players. So here the two blue players are playing against the two purple players. Notice that whenever one player from the same team, so whenever one purple player goes up, the other one sticks behind as a defensive player. But now look, they switch. When the other one moves up in an offensive move, the other player moves back in a defensive position. Very interesting learning from scratch. It's nothing that we programmed in here. Let me show you another example of 2-on-1 soccer. So people who play soccer will recognize this as a drill. So we have one player, the purple, is the goalie, and then we have two offensive players in the field trying to score on that goalie. And look, what is the best approach here? Well, the best defense apparently is offensive play. Keep the ball up, away from your own goal, and that's beneficial, clearly. So again, by playing, thousands, hundreds of thousands of examples here or episodes, the agent learns something relatively profound. Brings me on to traits in learning. We've talked a lot about how we recognize things. Look at this cute agent here. It's cuter than my little cubes, yeah? What would you call this trait? Yeah, it's basically cheating, yeah? Why should it why should it follow the maze if it can just crawl over? Yeah. So look at this next example. You remember the curriculum learning? We're trying to train the agent to push the cube next to the wall and use it as a stepping stone. But watch what this agent is doing during training. Yeah, now watch out. Yep. Just like an animal, it will find the path of least resistance. Clearly there was a bug in the environment here because it allowed the agent to just run around the wall. Yeah. So you fix that, you fix the environment, made it more restrictive, and the agent will have to learn to use the big cube as a tool. Yeah. But even in computers, we see cheating. Now, this brings me on to extrinsic and intrinsic rewards. A very, very interesting concept. Extrinsic rewards are, in the gaming world, things like capture, achieve, collect. It's specific to the environment. And we think of it as humans as sort of the getting rich concept. You collect points. There are intrinsic rewards in nature as well. We haven't talked much about them. Examples come from related to curiosity, impatience, patience, happiness, love, empathy, and so on. Nature invented these intrinsic rewards because they're beneficial. They're specific to the agent, not the environment. It's something personal. And we call those the getting happy rewards. Yeah. Now, let's cover this a little deeper. There are known limits to standard reinforcement learning. When you have very sparse reward spaces, like I like to compare them to Agatha Christie event chains. It's ridiculously improbable scenarios like this. We want the agent to enter a house full of rooms. In one of the rooms there's a button. It has to learn to push the button, and a pyramid will appear. In another room it will have to tumble the pyramid to collect the extrinsic reward, which is a gold cube on top of the pyramid. Yeah. Random exploration will not work. It's just too improbable that the agent will randomly learn this sequence. Yeah. So we have to favor agency over randomness. And the key lever we have here is nature's fantastic intrinsic rewards. Basically what we did is that we tried to define surprisal or curiosity in a mathematical sense. And the magic is right here. It's the reward. Normally in machine learning, we want to minimize the error rate. We want to make as good predictions as possible. Yeah. But in curiosity, you do the opposite in a sense. You try to figure out what you know the least about, to explore that first. Yeah. Let's see how that works out in an agent example. Here you have an agent in the room, in the house with all the rooms. Clearly, random exploration is not leading to anything here. You can let this agent try for 5, 10, 15 million episodes and just won't learn it. So let's try to turn on curiosity. We're not turning on the extrinsic reward, the getting rich reward. Yeah? We'll just see, what will a curious agent do? A curious agent is moving from room to room. Yeah? It will always try to explore another room. And it gets really curious here around what these piles of rocks or pyramids are doing. Yeah? And it figures out that if it actually hits them, something is going to happen. Yeah? Okay? Looks interesting. Now let's turn on the extrinsic reward. Yeah, it's curious and it tries to get rich. Learns to push the button. Now it's looking for the pyramid with the gold cube. There it found it. It knocks it over and come on, turn around, and there got the cube. Next episode, push the button, and so on. Yeah, you see, it becomes a much more efficient agent by using the concept of curiosity. Well, that is until you put a TV in there. You have the so-called TV trap, because the TV will always show something interesting and something new, and the curious agent will get stuck in front of that TV. So no solution is perfect. Let me take an example here from the gaming world. An NPC, it's a non-playable character. What we did is that we basically implemented a virtual robot dog, a robo dog, or puppy if you want. We put it in training camp to train a machine learning model for it to learn to walk, run, jump, turn, whatever it has to do to move around. So all the animation is trained, it's learned from scratch. The rewards function is very simple. It's return the stick. By returning the stick, that's the only way the puppy achieves a positive reward. Let's see what comes out of this. Here we have the dog, the stick. I throw the stick with my mouse here, so throw it, and the dog will run after it. The animation is not perfect, but it's not created by human hand. It's basically a small virtual robot here who learned to move. Whoops, it's not perfect, yeah? And it constantly tried to pick up the stick. I tried examples where I actually moved the stick left and right repeatedly in an attempt to see if I can get the dog to tumble. And once it happened to me that the dog basically grabbed the stick from me, which is actually what a real puppy would do. The rewards function here, or the desire to reap the rewards, are so high that it will do anything it can to get that stick so that it can return it to me. Yeah. So let's get back and talk a bit about how to get on the road to a greatly improved AI. Biology has a great trip in store for us. As you probably already can feel from my talk, we are looking nature over the shoulder. Yeah? We are trying to get inspired by looking at nature. And I'm going to show you a number of very specific areas here that is worth exploring. The first one is attention. It's basically, instead of seeing everything 360 around you, what if you only focus on what matters? Yeah? Nature developed this property to save energy. Yeah? We focus with our eyes on something and we don't see what's behind us, we don't see actually what's next to us. That's basically to limit the need for processing power. Yeah? So imagine cameras that only look at areas in their view that actually matters. Yeah? That would save a lot of energy. Think about self-driving cars where the cameras process more data from the front view than from the back view. Episodic memory, one-shot learning. There are clearly things where you don't need thousands or 100,000 episodes to learn it. You should really just need one. If you burn yourself on a candle, you probably, as a kid, you will probably avoid touching candles or touch the flame again. Yeah. Working memory. I showed you an example of long short-term memory, LSTM. There are other sorts of memory that you could explore along with reinforcement learning. Continuous learning. Continuous learning is very tricky. There's a trade-off. So if you're very good at learning new things, you're also typically very good at overriding them. Yeah, we see that in children. They can learn new languages very quickly. I had kids who, when we lived in Japan, were fluent in Japanese. We moved to the US. 6 months later, they couldn't count to 10 in Japanese any longer, but they were fluent in English suddenly. Unfortunately, when we get a little older, we're not good at that, at learning new languages. Yeah, the languages we learn, they get stuck. I can't run from my Danish accent. There's nothing I can do about it. It won't change. So the benefit of that, of course, is that then we don't really forget that easily either. Yeah. So continuous learning is a very interesting area to explore as well. Imagination, think about dreaming. That's really like running simulations. Yeah. And finally, we talked a bit about agency, intrinsic values. This is something that is a high potential area for research. Nature invented a number of intrinsic rewards or values for us humans and for animals. Curiosity is just one of them. It would be a very good idea to explore more of those. And finally, decomposition, hierarchical learning. A lot of the examples I show you are single model or two model examples, but what about 3, 4, 5 or 10 models? What about 100 models collaborating to achieve something? That's the very, very interesting topic of multi-agent system and multi-model systems. Huge potential for very interesting research there. Now, at the end of my talk here, I would like to step. We talked a lot about nature and biology. I would like to take a step and talk a bit about cultural evolution, because we have humans, Homo sapiens. We have also evolved over the years. We first appeared 200,000 to 300,000 years ago in Africa. About 100,000 years ago, we tried to migrate out of Africa, and we failed in doing so. Then we tried again between 45 to 70,000 years ago, and we succeeded, and we got all the way to Australia. Yeah. What was it that enabled that migration? First time it failed, second time it succeeded. A lot of people believe it's the cognitive revolution. Yeah. You see the figure here on my right, that's the Löwenmensch, or the lion human, found in Germany in the late 30s. It's made from a mammoth tusk, and you can see it's an abstract object. Yeah, it's a strange figure. Yeah. Researchers have actually tried to recreate such a figure here with stone tools, and they say it takes like 300 to 400 hours to do it. Yeah, so 35 to 40,000 years ago, someone did this figure, despite having to find food, despite having to protect themselves and their loved ones against predators. Yeah, they spend time creating an abstract figure. Yeah, that's an indication that something happened with humans over time, and just Homo sapiens itself here. Yeah, so let's think about this. There's no Moore's law for the human brain. Yeah, the last 100,000 years, we know from DNA that the brain hasn't really changed. Yeah, so no upgrades, no new GPUs, no magic on the hardware side, but lots of magic on the software side. So basically what happened is that over these 200,000 to 300,000 years, emergent behavior, language, collaboration, and anticipation of other people's actions were something that evolved in our software. Yeah. And this is the potential that we have with creating richer machine learning models, creating multi-model systems and multi-agent systems, is to have these AI systems learn their version of emergent behavior, language, collaboration, and anticipation. That was what I had for you. I hope you enjoyed it. You're welcome to link up with me on LinkedIn or follow me on Twitter. And of course, I encourage you to go out and download ML Agents and play with it and create your own AIs. I can tell you, as you probably saw from this talk, it's actually really fun.